Good morning all. Right, so today we want to finish the tree data structure, and also if we have time we want to start graph. That is our final data structure. Okay, right, so let's quickly finish our discussion on tree data structure. Right, so far we have discussed what is a tree, then we discussed what is a binary tree, then what is binary search tree, right? So we have discussed those things. So what is binary search tree? It's a tree where it is sorted from left to right. Okay, and then we discuss how to model a binary search tree using the node, right? Using the node where you have a data part as well as left child and right child. Okay, so it's again a node. It's again a node. So if you look at it from object-oriented point of view, it is two associations to the same class. Right? So this is your node class, and it has two associations. You can have multiple associations to the same class, right? So this is, we can call left child, right child. Okay, right. So then for the simplicity, we just model it using int, but I ask you to make it to a object as well. So the only thing is, if it is an object, you have to make sure that, because we have to compare things, right? We have to compare things when we insert, when we search, you have to take control of the comparing must be given to the person who is creating the node, right? So that is what I asked you to do, right? But let's continue with int for simplicity, right? For the rest of the stuff also. So then we implemented the insert method, right? So if we only keep track of the root, nothing else. If root is null, we just make the new node as the root node. Else, we have to keep searching from the root the relevant place to insert the node, right? So we have to go by comparing with root. If our new node is bigger, we have to go to the right. If our new node is smaller than the root, you have to go to the left. Then to that node also we do the same, right? So you keep doing this. You can implement it as a recursively also. We implemented using a loop. Okay, so you can easily implement using recursion. So that I forget to ask you to do that also. Implement the insert method using recursion, right? So we did that, and once we found that we have to go to right, but right is empty, then our new node is the right child. If we found that we have to go to left, and if the left child is empty or there's no left child, we just insert our one as the new left child of that node. So always your node will be added as a leaf, Okay, so that is what we did. Okay, that is what we did. Right, so that we implemented. So then we implemented the pre-order traversing, post-order traversing, and in-order traversing as well. Okay, in-order traversing as well. So we discussed that also. So I will not look at it again today. Now remember, you need to have a way out condition, right? And we implemented using the recursion. Right. So I asked you to implement the find method, find minimum value, and find max value method. Right. So I will quickly implement it because you had 1 week to do it. Of course, if you want to, if you had that attitude, motivation, you must have implemented it. Otherwise, of course, it is based on your attitude. So when you go to your final year, you will suffer. Okay. And also you will just get the degree, but not any competencies. Right. Right. So let's quickly finish the find min, because that is find min and find max are the easiest. So I will start with root node. I initialize to root node. Let's call it C or current. Right. So now what I have to do? Okay. For the time being, I will return a dummy value, return -1. Right. So what I have to do? I have to keep going towards left. So the leftmost node is the minimum. Okay. So while current is not equal to null, I have to go leftward. That's it. Simple as that. Current equal current dot left child, because I'm looking for the minimum. And when your current is null, actually when your current is null, it is too late. Okay. When your current is null, it is too late. That means then your previous is the minimum. Okay. So rather what you can do is you can check the current next. Okay. If current left child is null, right? So definitely you are in the minimum, or you are in the left edge. Okay. So what you can do is, if current's left child is null, right? So that means we are done. If currents, but this one also has a small issue. Right? Current equal current left child, but again, if the first one is already null, now we are in trouble. Right? For example, if this is your first, if you have only one node, then current is null. Current is null. So therefore, in that case, if current is null, it's a special case. You have to send it as empty. And there's another possibility. Current is having the data, right? But currents, that is the only data. That is the only data. But if that is the only data, that is fine, right? Because then current left child is null. So therefore, if current is null, let's implement it separately. If, or basically current is null means it's empty. Okay, it's empty. If, or you can say just root is null. If root is null, it's a special case. We can just say something like -1. So let's assume -1 means it's empty. Or you have to do exception handling, throw an exception. Okay. So let's assume -1 assumes empty. Assumes empty. You can write it as assumption. We are not doing exception handling. Rather, we return -1 if your binary tree is empty. Otherwise, you get out of the while loop when the current node has no left child. So that means you are in the leftmost node. So therefore, now I can send, in this case, current data, because current is not null. Right. So should it going to work? Do we have any bugs? I hope there are no bugs. Right. According to my understanding, we must not get any null point exceptions. Okay. So let's test this. Test it. Remember, we created a test class. We created this particular binary search tree. And of course, the leftmost one must be 5. Right? Leftmost one must be 5 because that is the smallest. So how did you add it? 70, 80, 30, 10, 40, 100, 5, 20. 20 is smaller than 70, smaller than 30, get a bit bigger than 10. So therefore 20 is coming here. 90 and 95. So if we have implemented it properly, we must get 5. Okay. Find min must return 5. Right. So let's do it. So this is our binary search tree. We have instance method called find min, and it will return the int, say min equal, and let's return it. Let's print it. Okay. Say min is min. Okay. Right. So we can test that. I think we have to build this because I just copied it. Right. So let's run it. We have run the test class. We must get 5. Okay, so it is not yet built. Let's build it again. Why are we getting an error? Still, it is not built. So I think now it's okay. Right. So let's see the answer. Right. Minimum is 5. So I forget the system out println. And they are. Let's run it. Right. Minimum is 5. So now you can implement the max also because it's a other same thing, but you have to go to the right tree. So you had enough time to implement these things. So I just copy paste this, find max. Right. Only difference is now you have to go to the right child because you keep going towards right. Right. Keep going towards right. Okay. And it should return the max value. In our case, the max value will be you have to keep going towards right. Right. So here you never come to the left side. So therefore the max value will be 100, not 95, because you go to the right child. If right child is null, that is your max. Right. If right child is null, that is your max. You never go left side. Right. So that's it. So let's test that also. Now you must be mature enough to do this kind of a implementation. Okay. So that is the objective of this degree. Build people with capabilities. Not someone with a certificate, someone with skills, competencies. Right? If things goes correct, I should get 100. Yes, I got 100. Okay. You keep going right. When your right child is null, that is your final answer. Right. Right. So that is the implementation of the min and max. Right. Min and max. Right. So then we have one more method to implement, that is find method. So checking whether particular value is there or not. If not, we can again return -1. Otherwise, we can return, or maybe we can return Boolean, yes. If found, we can say true. If not found, we can say false. Right? Right? It's super easy. Right? Super easy because we know that it is sorted. We don't have to search everywhere. You have to go in the relevant site only. So it's something like the insert method, but easier than insert method. Right? You don't have to create a new node. Right, so let's do it. So again, I need a node. let's call it current equal root. Okay. And let's say Boolean variable, Boolean is found, let's say false by default. Okay, by default false. Now we have to do is keep searching for that. While the current is not null, not equal to null. So if you have done this, you must have learned a lot of things by testing and so on. Okay. That is of course your task. Right. So I have to check whether if current dot data is equal to D, because we are using integer. Okay. If current dot data is D, is found is true. Is found is true. And of course, we can break the loop because we are done. Once you find, you don't have to keep searching. Right? You can say break. It will break out of the loop by the time your is found is true. So therefore, now we have to return is found. Okay. It will return true. Otherwise, remember now we have to either go to left side or right side because we are searching something and it is sorted one. So we need a efficient algorithm. We don't want to go and search everywhere. We want to go and search the best way. Right. So therefore, else if there is a current dot data, or let's do it something like D equal current dot data. That is better. Better presentation of the logic, because D can't be null as well. Right. If D is greater than, or let's say D is less than current dot data, sorry, current dot data, then your current must be current's left side, because we have to go left, because this is a while loop. So then again you will come and check whether the current is null. Okay, current is null. Okay. Right. Else, of course, if it is not same or not less, it's going to be greater than, right? So therefore I can say else, or you can just say else if also. So current equal current's right child. So that means basically current D is greater than current data, because those are the only three possibilities. That is, therefore I just use else. Okay. Right. So we keep doing that. And if you get into a null situation, that means we are getting out of the while. So that means the data we are looking for is not there. That is why we came to a leaf. Still, we haven't found it. Something like if you are looking for 50, say 50 is lesser, you come here. 50 is bigger, you come here. 50 is bigger, you come here. But you have come to a leaf or null. If you come to a null, that means 50 is not there. Because if 50 is there, you must have found it in your traversing. Okay? Right. So I hope this should work. I'm pretty sure this should work without any errors. And because we have covered the null situation also. Right. So by default, we make it false. If we found only, if we have found it only, we have make it true. Right. So let's search it. Let's test it. This time it must return a Boolean value. Say Boolean. Or you can just call it here itself also. Say search S1. Say we are looking for, let's search something which is already there. Let's say we are looking for 90. And it must return true because 90 is there. Okay. Right. So let's run it. And we must not get any null point exceptions and so on. Okay. It says true. Yes, it has to be true. Right. So now let's search something which is not there. Like you don't have 50. Okay. You don't have 50. And we must get false. False. 90. This is 50. So we must get false because there's no 50 there. Yes, it says false, right? So likewise, you can test for the 70 special case, something in the middle, something in the leaf. Likewise, you have to look at different scenarios and test. Okay, right. So that's it about the basic method. What are the methods we implemented? We implemented the find method. Of course, we have already implemented the insert method. So we implemented the find min method and find max method. Okay. Right. Another method I want you to implement is finding how many elements are there. Right. Count elements. Of course, that you can do it in different ways. Right. So I will give it as an exercise. Maybe they can ask you to implement it in their exams. So this is another one. Int find count node. So total nodes that you have to implement. Okay, I will return -1 for the time being. That is another exercise. Of course, this can be implemented in multiple ways. Okay, multiple ways. So those are the possible things, right? So basically, this subject is all about not teaching you about trees. Of course, learning about trees is also good. Give you opportunity to develop your problem solving skills, right? Because we need, in the society, we need problem solvers. We have plenty of problem creators who live in other problems, right? So especially Sri Lankan society lack who can solve problems. Okay. So the doctors are solving problems, right? So when you go with a lot of pains and so on, so the doctor solve your problem. Right? So that is why we respect that guy, right? Not because that guy has a degree or whatever, because that guy solve problems in the society. Right. So our next method is, which we don't implement, not because we can't implement, of course we can implement. We have to consider different scenarios, case by case implement. That is deleting a node. Right? Deleting a node. Okay, so let's move on to delete. I will come back to traversing later because we want to implement it using stack and queue also. Some of the traversing methods. Right. So let's look at the delete method. So when it comes to deleting a node in binary search tree, there are three possibilities. Right? There are three possibilities. The first possibility is, just give me 1 minute. Okay. So the first possibility is, let me open OneNote. So today we want to finish this, okay? And also we want to start to graph. I'm just waiting for the one node to appear. Right. So when you delete a node, there are few possibilities. For example, let's assume we have 80 here, 50 here, 100 here, 20 here, 30 here, 40 here, say 90 here, and 85 here. And here, let's assume we have 120. And maybe 110, and maybe, yeah, so something like that. Okay, right. So there are three possibilities. So the first possibility is the node that you want to delete. Now you can see this is a binary search tree. So the first possibility is the node that you want to delete is a leaf node. Leaf node means it has no child. Okay, so something like this. Right. Something like this, something like this, something like this, something like this. So if you want to delete, first of all, you have to find out the node to be deleted. Now we have implemented this find method. So you can use that part. Okay. Right. Any question? If it is left side, 50 cannot be next to 40. Oh, is it? Yeah. No, I didn't get your question. Okay. What is your question? If it is left side, of course, 50. Yes. Yeah, got it. Yeah, got it. So let's make it something else. Okay, right. So I made a mistake. So let's make it something like 60. Right. Thank you for that. Okay. Right. So if you want to delete something like this leaf node, it's super easy. Once you find it, you simply delete it. You simply delete it. So that is our scenario one. And that is the easiest to implement. That you can implement. So now this is something you have to implement. No point me implementing, right? Because now I have showed you how to implement min, max, insert, find. So the objective of education is not to give you exams and check whether you pass it. Objective is give you that competency, courage, okay, your character, right? So you must be able to implement that scenario, right? So that means you keep searching that value, and you find that its left child is also null, right child is also null. So that means it's a leaf node. So now what you have to do? Right? What you have to do? How do you implement that part? When you search it, and you can use the find method, and then you find that your left child is null, right child is null. So that means the node to be deleted is a leaf node. So then what you have to do is you have to keep track of the previous. In this case, you better take the previous also. So then you have to say, if you are the previous right child, in the previous step you came to the right, then you have to make sure that the previous right child is null. So that means effectively you delete this. Right. So therefore, when your current is here, your previous is here. Right. And if you came right side in the previous step, what you have to do is previous right child is null. And if you came something like here, your current is here, your previous is here. And you have to keep track of whether you came left or right. Now here we came left. So therefore the previous left child must be null. So that means you are deleting this. So that is very easy. That is how you implement the delete in case the node to be deleted is a leaf node. Okay. Right. So that you must be able to delete, implement without any issue. Okay. Right. So that is scenario 1. That is the easiest scenario. Okay. That is the easiest scenario to implement. Right. So now let's take the scenario 2. Right. Scenario 2 is the node to be deleted has one child. So what kind of nodes are that? So this one. Node to be deleted has, it doesn't matter whether left child or right child. Okay. So this is having 2 children. This is having 2 children. This is obviously having 2 children. So this is no children. Right. So this one is another one having only 1 child. This is another one having only 1 child. So this one has 2 children. So if you want to delete this kind of a scenario, or this, say that now your task is delete this node, right? Or delete this node, or delete this node. So let's add few more nodes here, say 115. Okay. Right. So again, this is relatively easy task, right? Relatively easy task. Again, what you have to do is when you take to the current, say this is your current, and now you have found that this is what you want to delete. We don't know how many elements are there, right? Maybe again you have, okay, so this is 30. Again you have 25. And again maybe you are having 35 and so on, right? But definitely you can see this one has only 1 child. And this is the one that we want to delete, right? This is the one we want to delete. This is the one we want to delete, right? So it's super easy. What you have to do is, if you have a right child or whatever the child, it doesn't matter. You have to make sure that you have only 1 child now. That child, your parents' relevant child must be your child. If you have a right child, make sure if you are the left child, say you are the left child. In this case, you are the current is the left child of the previous. Now remember, we have to take the previous also. If current is the one that you want to delete and you are the previous or your parents' left child, make sure your parents' left child is your child. Right? That's it. ඒක හරියට ඔයා මැරෙනකොට ඔයාගේ දරුවෝ ටික බලා ගන්න කියලා එක දරුවයි ඉන්නේ ඒ දරුවෝ බලා ගන්න කියලා අම්මට කියනවා. එච්චරයි. Simple as that. මොකද ඔයා මැරෙනවාද? Because you are the left child, you have to ask your parent node to consider your child as your parents' left child, because you are the left child. So that means basically you are creating a link like this, right? And this link is not there, and this link is not there. So that is what happens, right? Say this one you want to delete. So then you have to make sure that you are the right child of your parent. So therefore, basically what you do is you delete this and let this guy link to this. Simple as that. Okay. Right. That is how you delete a node like that. So here you are the left child of your parent. So therefore, let your parent connected to this one. And again, you can see that the binary search tree nature is not violated. So the idea is delete the node without violating the binary search nature. At the same time, make it as simple as possible. Right? Make it as simple as possible. So the only property we want to preserve is it is sorted this way. Okay. So there can be some other ways to delete, but we are interested in the simplest possible way. That is the most efficient way. Okay. Right. So I forget to give you that there's a link I wanted to share to you. I'll put it into the WhatsApp group. So which is really useful for you to understand concepts by experimenting. Okay. Just keep that link with you, which will be really helpful. And there you can go to the binary. There's a binary search tree. Yeah, binary search tree. So binary heap will be doing next. So just have to say next, and done. Right. So, for example, let's create a random. Right, let's create a random binary search tree with say 10 elements. Random. Right. So why we have 36 two times? Right, we have 36 two. Do we have 36 somewhere else? No, right? Okay, let's create another one. Okay, I just want this one is better. Okay, so it just create a random trees. Right. So now I want to delete, say this one. 3. It's super easy. Just make your parents left child null. Okay, let's delete it. Right. Remove 3. I'm deleting this one. Okay, it's a leaf. So it's keep searching. Right, and it find that it has no. Yeah, just simply remove it. That means your parents right left child is null. Okay. Now let's see, I want to delete something like this. You can see that is our second scenario. It has only one child, and you are your parents' right child. So therefore, you have to ask your parents to consider your child as its right child. So that effectively delete 84. Okay, let's delete 84. Okay, so it's now keep searching. Right now it found that it has only one child, right? So that's it. Simple as that. Okay, simple as that. Okay, so let's create another random tree because we deleted some of those. Let's make it a little bit more. Say 15 elements are there. Right. So 15 elements are there. Say I want to delete 79. Okay, let's say I want to delete. Okay, let's create a different one with a little bit more things. Right, I want to delete 57. Okay, so let's say I want to delete 57 and 57 has only one child. Right, so therefore now what you have to do? You are your parents' left child. So therefore now your parent has to consider your child as the left child. Of course, that is your right child, but you are your parents' left child. So therefore 66 has to consider 63 and all the other things as, of course, all the other things will be automatically connected. This will basically what it does is it will consider this guy as the left child because you are the originally left child, and that effectively delete these things. Okay, right. So let's delete 63. 63. First it has to search 63. Right. Right. Still found. Sorry, not 63, right? We wanted to delete 53. Sorry. So let's insert 63 again. Sorry for that. Okay. Now, of course, 63 will be added to the other place. Okay. So we can't, unfortunately, we don't have the undo. Right. Undo. Actually, I wanted to delete 57, not 63. Okay. Okay. So let's delete 47. So therefore, 47 is having only one child. But 47 is the left child of 49. So therefore, 70, I don't know why this called 17, 2 will be the left child of 49. Okay, so let's delete 47. So you can do that type of experimentation and learning. Okay, if you haven't Right. So it has only one child. So that's it. Simple as that. Rest of the stuff are not affected. Okay. Rest of the stuff are not affected. So again, you should be able to implement this. So I just keep it as exercise. Okay. So it may take about 1 hour. It doesn't matter. Okay. So when you solve problems, we can't solve problems, every problem in 1 hour, right? Just like a surgeon will do a brain surgery for maybe 5 hours, transplant surgery for 10 hours. Okay. Right. So that is the scenario 2. Scenario 2. So let's create another binary search tree, random one. Right. So that is good. Nice one. Right. So the scenario 3 is the node to be deleted has 2 children. Right. For example, this is the node I want to delete. Now you can clearly see that I want to delete this, but it has two children. So if you have 2 children, you have to find in-order successor or in-order predecessor. Okay. So in-order predecessor or in-order successor, it doesn't matter. So this is how you find the in-order predecessor. Now this is the one I want to delete, because when we search, we found that this is where the node to be deleted. Now you have to go left only once, right? Only once. Then you have to keep going rightwards. Keep going rightwards. Okay. And of course, here only one right element is there. Then you don't have anywhere to go. You have to keep going rightwards only. Okay. Now, what you have to do is you have to replace the node to be deleted by this one. Simple as that. So that means you have to replace 24 with 18. Then 18 is no longer there. That is if you do the in order predecessor. Now again, you can see it's binary search tree 10, 17, 18, 28, 32. So we want to preserve it. The second approach is you can use any of the approach. You find the in order successor. In that case, you have to go once right, then you have to keep coming left. Of course, here you don't have anything to come because there's no left. Then you replace this one with 18. In that case, of course, this will be there. Okay, this will be there because you have to do one of those. Then you replace 24 with 28. Okay, so either that can happen, this will be replaced here, or this will be replaced here. Of course, you don't have to implement both, you can implement one of those. Okay, now let's see whether it is doing like that. So I want to delete 24. Okay, 24. It will use one of those approach. Right, it went for the in-order successor and it replaced with that. So then of course this is not touched. Now again you can see it is the binary nature is preserved. Okay, so it's look like the way it is implemented is it is looking for the in-order successor. Okay, right. So now let's delete 38. Now what is the in-order successor? Because this one has implemented using in-order successor. So this is the one I want to delete. So you have to go one right, then keep coming left. Only one right. Okay, one right, then keep coming left, and if you don't have anywhere to go left, that is your in-order successor. So therefore 40 will come here, 38 will be removed, 40 will be there, 40 will not be here because 40 will be there. Then you can see 33, 40, 43, 48, 65, 82, 89. Right, so let's delete 38. If you have any doubt, do some experimentation with this. Say, I want to delete 38. Okay. See 38. Yeah, 38. I want to delete 38. Okay. So this 40 will replace 38. Now it has found it. Now it will keep looking for the in-order successor. Keep coming left. Right. Found it. Replace it. Okay. That's it. Or you could have replace it with this one. That is right in order predecessor. You go once left, then keep coming right, but there's nothing to go rightward. So therefore that also work. So you don't have to do both. You can do one of those. Right. So any questions? Okay. So let's create a little bit bigger tree. Let's say 20 elements. Right. So can you remove? Can you remove? So 68 is the root. Right. 68 is the root. 58. Of course, 58 has 2 children. So you have to find the in-order successor or in-order predecessor. This algorithm has implemented in-order successor. So that means you go one right, then you keep coming left. You go one right, keep coming left. Don't go right more than once. Only once you go right, then you come in left. There's nothing to come in left. So that means your in-order successor is this. So 58 will be replaced by 60 and 50. Then of course 61 and 62 will be there. Okay, let's delete 58. It's searching for 58, found it. Now it is searching for in-order successor, found it. That's it. You come one left, right, then keep looking for right. Sorry, one step right, then keep looking for left. Don't go more than one step right, okay? In-order successor. In-order predecessor, just go one step left, then keep going for right. If there's nothing to go, you are there. Right, that is how you did it. So I just keep it as an exercise for you. Right. So you need to you have 3 scenarios, right? So those 3 scenarios you have to implement, and you can just return true or false, because if it is not there, you can't delete, right? So true means you have successfully deleted. Then again, you can do a traversing and test whether it is no longer there. Like you can do in-order traversing and see whether it is there. It should not be there if you have properly implemented it. Okay. Of course, in the exams, they don't ask you to do that because this is a lot of work, but this is for your, because when you're doing software development or IT field, they don't give you exam and give you the salary, right? You go every day, you go to the work, right? Maybe, right, from 8 a.m. to 5 p.m. you are doing software development. So don't think that you get hello world software. And not only you, set of people, right? Maybe 10 people get together and developing the software. Okay, right. So let's say Boolean delete. So we'll tell that value int d. So you have to return true or false. Not only that, you have to delete it. Okay, so there are 3 scenarios. This is the out of these implementation, this is the most challenging one. But it doesn't mean it is impossible. Okay. I will hard code to false. Okay. So you can just have Boolean variable, Boolean is deleted. So if it is found only, you can say yes. I'll say false by default. Now it's return it, but you have to implement it. Okay, you have to implement it. Right. So that is how you delete. I explain you the logic. You have to implement. You have to implement. So that is what happens, right? In software development also, your architect, sometimes he will explain the logic. But architect is not going to implement it because the architect has some other work. Right? He is the architect. He is the designer. You are the developer initially. Then one day you can be the architect. Of course, if you like that kind of challenging careers. Some people like challenges, some people don't like, right? So some people they are trying to go to Mars, right? So they are working with space station. So that is what their life. So they have big objectives in their life. They like to take big challenges. So not everyone is a small person, right? So now we are done with deletion also, right? Deletion. So the code is not given because that code is something you have to develop as an exercise. Right. So now we move on to another few theory parts. What is mean by full binary tree and what is mean by complete binary tree? Because we need those two concepts later on when we do binary heaps and so on, balanced binary tree and also binary heaps. Right. Super simple concept. A full binary tree is where each node has either no child, no children, or two children. So that means you have no node having one child. Right? No node having one child. Something like this. This one has two children. 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 But these one they don't have any children. Right? For example, this one. So this one has two children. Two children. This one has no children. That is fine. So this is a full binary tree because this one has two children. This one has no children. This one has two children. This one has no children. This one has two children. This one has no children. No children. It's a full binary tree. Okay, full binary tree. Okay, that's it. You have to check whether each and every node, whether it has a full two children or no children. So that also you can implement if you want. Right? Return true and false, true or false, whether it's a full binary tree or not a full binary tree. Of course, after you create your tree. Right. So the next one is complete binary tree. In a complete binary tree, each level, so this is level 1 and so on, other than the last level, okay, are completely full. So the last level, that means this must be full. This must be full. The last level means this one actually, not this one. This level, it may not be full. You can see this one has one child, so therefore it is not full. But that relaxation is only for that level. And also there's another condition. It must have filling those children from left to right. Left to right. So therefore this is a complete binary tree because only this one level has a one child, but you can see that all its left siblings are again having two children. So basically, so the next one must be something like this. Next one must be something like this. But if you have something like this, it is not complete binary tree. Say you have two here and you have something here. So this is not a complete binary tree because this one has only one child, but this one, it is not filling from left to right. So this one has no child. So therefore, this is not complete binary tree. If this need to be complete binary tree, first of all, these two has to be filled. So therefore, how do you create a complete binary tree? It's super easy. This is how you do it. You just keep adding like this. Right? So always at any time, this is a complete binary tree because I keep adding from left to right. I don't just go somewhere here. No. So it's a complete binary tree. Okay. So if you maintain that, we say that it's a complete binary tree. Okay. Right. So these are some exercises. Now, for example, this one, definitely it is not a complete because without filling these things have been filled. It's not complete. It is not full also because you can see it has only one child. Okay. So you must have always two children or no children. So this one again, one children is there. Right. But it is complete because it is filling from left to right. Right. So this one is full because every node has either two children or no children. But you can see it is not complete because without filling these, it has filled these. And this is both complete and full. Okay. Right. Right, now we move on to our final subtopic related to binary search tree. Of course, then we have the binary heap. Okay, that is balanced binary tree versus unbalanced binary tree. Okay, right. So that is a little bit long story. How to balance it? We have two type of rotations and so on. So the exam in the exam they have given you these kind of questions and ask you to explain how these rotations are happening in the second paper. On to uh, balanced binary tree. Okay, balanced binary tree. So what is mean by balanced binary tree? Okay. So balanced binary tree is sometimes when we insert data. So let's take an example here. So let's create a new tree, empty tree. Right. So let's say I want to insert something like say 40. Okay. So the 40 will be the new root. So let's say I want to insert say 50 or let's say 70. Not insert, right? 70. Right. So 70 is bigger than 40. Okay. So now I want to insert say 20. Of course, 20 will be in the left hand side. Okay. Say now I want to insert say 80. Okay. So it will go there. Say now I want to insert 90. So I'm just inserting things. Now you can see that this binary tree is growing. The one side is growing, other side is not that growing because the way I am inserting data. So now I want to insert say 70, 85. So you can see it is not balanced. The right side is having more elements. The left side is having less elements. So therefore, this is not balanced. So the idea about binary tree is have less levels. Now here you have already, this is one level, second level, another level, another level. 1, 2, 3, 4. Right? So height 1, 2, 3, 4, height 4. And this is height 5. So that means when you are searching for something, I have to go this. But if the elements are sort of a balance, with less levels, we could have keep all these data. So the balanced binary tree is, we try to balance is, if it is getting out of balance, we again readjust it. Because in a binary tree, binary search tree, only requirement is it is searched from left to right. Right? It is sorted from left to right. So therefore, the moment you feel like it is unbalanced, we then and there adjust it. Then and there we make it balance. So that is what balanced binary search tree is. Balanced binary search tree. There are different ways you can make a binary balance search. It is not that we make it unbalanced and balance it. We don't let something like this to happen actually. The moment it is slightly unbalanced, we want to fix it. We don't want to make it worse. Okay. So there are different techniques for that. So the two most famous or the popular techniques are AVL tree and red-black tree. AVL balanced binary search tree, red-black balanced binary search tree. In your syllabus, they have mentioned only AVL tree. Right? AVL balanced binary search tree. Okay. So the idea is when it is getting out of hand, we adjust it. We adjust it. So that every time, any moment, it is balanced. Okay. That is the idea. Right. So now let's see how to create an AVL balanced binary search tree. So in order to understand that, first of all, you must know what is mean by balanced binary search tree. A balanced binary search tree is where a binary search tree of which its balance factor is always either 0, -1, and +1. You never let it go beyond that. Right? You never let it go beyond that. The moment it is beyond that, we fix it. So therefore, the worst case is you get into something like -2 or +2, but the moment you get it, you again make it something like this. So therefore, it will never go to something like -3 +3. The moment it is -2 or +2, we again adjust it. Okay. So what is mean by balance factor? Balance factor is calculated for each and every node. It is not the property of the tree. It is a property of each and every node. Balance factor. Right. So balance factor is for a particular node is its left height minus right height. Left height minus right height. So the easiest way to understand this is, now for example, this one. Now if you look at this node, it has no left child, no right child. So the balance factor is 0. If you take this one, its left height is 0, no child. Right, we have 1. So that is this side 0, this side 1. So 0 minus 1 is -1, -1 is okay. So therefore this is balanced. That means this node is balanced. If you look at this one, your left is 0, right is 2. 0 minus 2 is -2. -2 is not allowed. It's only 0, -1 and +1 allowed. So therefore, at this node, it is not balanced. So you always check the balance from leaf node towards the root, not from the top to bottom, bottom to top. So therefore, this node is unbalanced. We need to adjust this node. Of course, this node is also not balanced because this side it is 1, this side it is 1, 2, 3. 1 minus 3 is -2. This is also not balanced. This is also not balanced, but this is okay because 0 minus 0 is 0. This is okay. 0 minus 1 is -1. This is okay. It is 0. So this is 0. This is -1. This is -2. This is -2. This is 1. Sorry, this is again 0. Okay. But remember, we fix not the top from the top. We fix it from the bottom or from leaves. So therefore, we don't fix this one. Rather, we fix this one. Okay. We fix this. That means we have to adjust this node to make it again balance. Okay. Make it balance. So this is after making it balance. This one we have make it balance by doing rotations. So basically what we have done is we have taken 2 rotations and make it balance. Now you can see this is balance factor is 0, 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 because 1 minus 1, balance factor is 0, and here also balance factor is 0. Of course, even the balance factor -1 or +1 is also okay. Okay. So -1, 0, +1 now okay. But if you get something like -2, +2, it is not balanced. You have to adjust it. Right. How do you adjust it? How do you balance it? So there are 2 types of rotations. So what is known as right rotation and what is known as left rotation. So that means either you have to do a right rotation or you have to do a left rotation. Okay. So this is how you do a right rotation. Right. To rotate right side, right hand side. Okay. Or clockwise. This is how you do it. Your B will come here. You can see B has come here. Then D goes down. D goes down, and when D goes down, E also goes down with it. Right? So B came here. With B, A also came. Because when B came here, with A also comes here. But there's a special case. That is, when you do that rotation, right? You do the rotation here. The right child of B has to become the left child of D. So that is super important to understand. So you can see the rotation is happening like this. You can see the right child of B, which is C, which is originally connected to B. Now B is in the upper layer. Now that C has become left child of D. So this is the important thing to remember. Earlier it was the right child of B. Now B is in that pivot. So it has become left child of D. Okay. So that is super important. Other than that, it is just rotation. Just rotation. Just you rotate it. While you are doing rotation, your right child of the left must be the left child of your right. Okay. And of course, if you are doing the other way, there is your original situation is like this. So then you may have to do a left rotation, right? Left rotation. Again, you just rotate it. D goes up, B goes down, and E comes with D. But remember, your left child of D is now right child of B. Left child of D will be the right child of B. So that is the super important thing. Okay. Other than that, it's just a rotate. It's just a normal rotation. Only thing is you keep track of what happened to this child. This way what happens, that way what happens. Okay. Right. So by doing either left rotations or right rotations, sometimes you have to do it once, sometimes you have to do it twice. You can make it balance. Right. You can make it balance. Okay. If you don't understand this, you will not be able to write the answer. You have to explain this and write it. If you have gone through the past papers, you may have seen that kind of questions. Right. Now let's look at what are the scenarios. Now you know what are the two types of rotations, right rotation, left rotation. So we are talking about the AVL trees, okay? We are talking about AVL trees. Right. So what are the two scenarios? Actually, there are 4 scenarios or situations. One scenario is you get into this kind of a situation. So you see that there's an imbalance node here because this is 2 minus 0 is 2. 2 is not valid. So therefore there's imbalance here. This is okay. 1 minus 0 is 1. This is okay. 0 minus 0 is, this is balance factor 0. This is balance factor 1. But this is balance factor 2. So therefore this has violated the balance factor. Okay. If you get into this kind of a scenario, forget about the rest of the stuff. Okay. This is called left case. Left. Imbalance is here. Imbalance is due to left scenario. You don't have right value. So then you have to do just one right rotation. Right rotation. So then 5 goes down, 4 comes up. But remember, the right child of 4 become the left child of 5. Right child of 4, which is C, has become left child of 5. That is a super important thing to remember when you do that rotation. So this is something you have to keep it in mind. Other than that, it is just a rotation. Okay. Now the other scenario is you get into a right situation. So again, this one's balance factor is 0, no children. This one's balance factor is 0, minus 1, minus 1. Minus 1 is okay. But this one's balance factor is 0, minus 2, minus 2. So this has violated. So this is imbalance. Okay. So then you have to do a left rotation. When you do the left rotation, just do the left rotation. 2 comes down, 4 goes up, 5 comes with 4. But remember, the left child of 4, which is B, will become the right child of A. You can see left child of 4 has become right child of 3. Okay, that is super important to understand and remember. So this is how you make this into balance. Left situation, you have to do a right rotation. Right situation, you have to do a left rotation. Right, left rotation will make it balance. left situation can be balanced using right rotation. Right rotation. Okay, got it? Right. So then there are another two situations. So now this is a balanced situation, okay, after the rotation. This is unbalanced, we balance it. This is not balanced, we balance it. Then there's another possible imbalance situation. That is something like this. So this is called left-right scenario. Why we call it left-right? So this is not balanced. Of course, this is balanced because 0, no child. This is also balanced. 0 minus 1 is minus 1, fine. And this is not balanced because left side you have 2, right child 0. Right, 2 minus 0 is minus 2. So therefore, this is not balanced. Okay. Now, when you have imbalance with left-right scenario, first you have to do a left rotation and make it left-left. So this is where you need double rotation. So you can't straight away fix this. So your first step is, when you see this kind of a scenario, your step number 1 is you do a left rotation. You do a left rotation and make it to a left-left scenario. Still it is imbalance, but this is your step number 1. So then again, remember, your left child of 4 will become the right child of 3. So this B, left child of 4 will become right child of, remember that is B, it will become the right child of 3. Okay, so that is super important. 4 goes up, 3 goes down. With C comes with 4, but this B has disconnected from 4 and it has connected to 3. Once you get into this, now you have make your left-right situation into a left-left situation. Now, left-left situation, you know how to solve it by doing a right rotation. By doing a right rotation, you make it balance. So therefore, this kind of a scenario, one rotation will make it balance. But if you have a left-right scenario, first you do a left rotation to make it a left-left scenario, and then do a right rotation to make it balance. So this scenario, you need 2 rotations. First make it this and this. But this scenario, you straight away make it balance. So the same thing can happen the other side also. If you have a right, don't worry, just one rotation will make it balance. But if you have a right, left, first you have to make it right by right rotation. Right. So again, 5 goes down, 4 goes up, but make sure the right child of 4 will become the left child of 5. Okay, so C will go down. Okay, that is something you have to understand. Once you get into that scenario, again, you can do a left rotation and make it balance. So these 2 scenarios, you need double rotation. These type of scenarios, you need a single rotation, because these kind of scenarios, you can fix it by first coming to this type of scenario and then balancing it. Okay, and it's initially you may feel like it's a big thing. Yes, I know, but with experience, after sometimes you will find that no, that is not that difficult thing. Right? It's not a difficult thing at all. Okay. Right. So let's take an example. Right. So this is my first element 50. Remember, this is a binary search tree, but we want to make it balanced. So we want to make it a AVL tree. Next, of course, first I have 50. That is fine. It's balanced. It's 0. Balance factor is 0. Now I want 20. Of course, 20 will go there. And this one's balance factor is 0. This one's balance factor is 1. 1 minus 0. 1 minus 0 is 1. 1 is fine. So still this is balanced. Still this is balanced. Now I want to insert another element. See, I want to insert 30. Remember, by the definition of binary search tree, you come here, 30 is less than 50. 30 is bigger than 20. So therefore 30 will be here. Now you have to check the balance factor from this point onwards. So this point's balance factor is 0. 0 minus 0 is 0. Fine. This point's balance factor is 0 minus 1 minus 1. Fine. Minus 1 is fine. But what about this point balance factor? This side 2, height is 2. This side height is 0. 2 minus 0 is 2. 2 is invalid. So therefore, the violation is here now. You have to check the violation from that point on upwards. So the violation is here. The violation is here because the balance factor is 2 for this node. And you can see it's a left-right scenario. It's a left-right scenario. Left-right scenarios need 2 rotations. First, you make it left-left. Then you make it balance. So how do you make it left-left? By doing a left rotation. So 30 will go there, 20 will come down. So therefore, the result is 50, 30 will go there, and 20 will come down. So that is my first rotation. You have to draw this like this and say, this is the result. Okay. Now it is a left-left scenario. Still, this is not balanced. This is 2. Now you can do a right rotation. So 30 will go up. There's nothing to hang. There's no hanging ones that we want to fill it to there. Just a simple rotation. So 30 will go there. 20 will be here. 50 will be here. And that is my final after the double rotation. Okay. After the double rotation. So this is the final result. 20, 30, 50. Now let's say we want to insert 10. Of course, insert, you can add it as the left child of this. But that has not violated the balance factor. Oh, it's still balanced. It is still balanced. Why? This one's balance factor is 0. This one's balance factor is 1. 1 minus 0. This one's balance factor is 2 minus 1, 1. This one's balance factor is 0. So perfectly okay. Still it is balanced. Okay. So now you can insert another one. If it is balanced, you don't have to do any rotations. Say, I want to insert 5. 5 will go there. 5 will go there. Now you can see, again, you have to check from that point upwards. Right. So this one's balance factor is 0. This one's balance factor is 1 minus 0, 1. This one's balance factor is 2 minus 0, 2. This has violated. So this is where the violation. Of course, this is also violated, but you check from bottom. Right? You do the fix to the correct place. Now this is left-left scenario. Left-left scenario need only one rotation. That is a right rotation. So therefore 10 will go up, 20 will go down. Right? So therefore the final result is 30, 50. This is where the rotation is happening. 10 goes up, 20 goes down, and 5 comes with that. Now again balance. Because this is balance factor 0, balance factor 1, balance factor 1, balance factor 0. Right? So you can see it's keep adjusting, right? So that is your final result. Now you want to insert 3. 3 can be safely inserted here, but now we are again in trouble. Why? Now 3 has been added. Now this one's balance factor is 0. This one's balance factor is plus 1. This one's balance factor is 2 minus 1, 1. Right. So this one's balance factor is 1, 2, 3 minus 1 plus 2. So now the violation is here. Right. You have to just check in this part because that is where the imbalance can happen. Right. When you add something here, there won't be imbalance here. You just keep coming from that point towards the root. Okay. Right. Now, this is not balanced because this is 2. And you can see that it is left-left scenario. You have to look at the imbalance side. Right. Left scenario. Don't worry about this. It's a left-left scenario. That means you need single rotation. But now you have to be careful because this guy has a right child. Okay, so therefore, when you rotate, 10 goes there, with 10, 5 and 3 will also come, but this 20 will be, the right child of 10 will be left child of 30. So therefore, 20 will be, the 30 will be down and 20 will be the left child of 30. Okay, when you do the rotation. You can see 20 is the left child of 30. Others have just come up and now it is balanced. Now it is balanced. Why? Because this one's balance factor is 0. This one's balance factor is plus 1. This one's balance factor is 0. This one's balance factor is 0. This one's balance factor is 0, 0. Okay. That's it. So that is how you have to keep doing this. Whenever you do insert, you check the balance in that path. In that path, you don't have to check that in other path. Okay. Right. So let's do an exercise using our online tool. I will go for the AVL tree. This is the normal binary search tree. This is AVL tree. Okay. So this is already created. Let's create from the fresh. Okay. So let's create an empty one. Right. Now let's insert one by one. So let's say I want to insert 50. So 50 will be the root. Right. So now I want to insert, say, 30. So 30 will be added to the left and it is still balanced because balance factor 0, balance factor plus 1. Let's insert. You have to do this by yourself. So now let's add, say, 20. Well, let's say, yeah, 20. Now 20 will be added this way. Now the imbalance is not here, imbalance is here. And it's a left-left scenario. Single right rotation will do it. Okay. So 30 will come to the root. Right. You can see. Now the rotation will happen. Right. 30 came to the root because single rotation will do it. But there's no hangover things to transfer to the other side. Okay. Of course, in the animation, you don't see the double rotation. It will be done as a single step. But in reality, we do it as a double rotation. Okay. Right. So let's insert, let's say we want to insert 15. Sorry, 25. And 25 will be added as the right child of 20 and there won't be any imbalance. There won't be any imbalance. So no rotation needed, right? That's it. It's not rotation, just added 25 and it's checking the balance. No issue. So this one's balance is factor is 0. This one's balance factor is -1. This one's balance factor is 1. 2 minus 1 is 1. This one's balance factor is 0. Now let's see, we want to add, say 24. Okay, so let's say 22. Okay, now let's look at what I'm doing. 22. Okay, and I will say go. Now look at it very closely. First, it will be inserted. Right. So that is done now. Now insert is done. I stopped it. Okay, I stopped it. Now I'm going to do it with my control. Now it will check the balance factor. Balance factor is 0. Balance factor is 1. No issue. Here balance factor is 2. Right. So let's go there. Right. Balance factor is -2. Sorry. 0, -2, -2. Now this has violated. So you don't go. If there's a violation from your path to the top, you stop there and fix it. Now balance factor is -2. And you can see that it is a left-right scenario. Right-left scenario. Right-left. Right-left. So that needs to double rotation because it's sometimes in your exam paper, it's called dog foot scenario. Crook scenario. Balon kakul adaine. Dog foot scenario kila kiyana api. But better thing is right-left scenario. Now you need a double rotation. First, we want to make it right. How to do that? By doing right rotation. So that means your 22 will come here. Right? So that is your first rotation. Then it is right scenario. The issue is here. Right scenario. Now you have to do a left rotation. So that will make 25 comes here. That is the final result. 25 comes here. Okay. The 20 goes down. And with 25, 22 will also come. And 22 will be something like that. Okay. So that will fix that. But again, now this part is okay. But now the issue is here. Because its balance factor is 2. 1, 2. No, that is fine, right? So 1, 2, 2 minus 1 is 1. No, now that is fine. So therefore, the final result is 25 will come here. 20 will be there, 22 will be there after double rotation, but you will not see the double rotation. You will see it as a single thing. Okay, right. So let's let it go to the next step. Right. Now we can see. Now you can see. No, you can see the first rotation. I thought that you can't see the first rotation. Now you can see that the first rotation is done. Now it is a right scenario. Now it will do the left rotation to make it balance. Okay, make it balance. Okay. Now it will do and now it is doing the other rotation. Right. Now we got into that. Right. Now it is balanced. Okay. 20. I think I made a mistake somewhere. I made a mistake. Okay. I think I made a mistake somewhere when I explain it. So, okay. So therefore, let's do it for another one. Okay. Now anyway, it's balanced. Now it's balanced, but the result is slightly different. Okay. Now let's do another one. Now let's make it another imbalance situation. So I want to add, say 27. So this is fine. This is fine. This is also fine. Okay. This is also fine because this is balance factor is 1 minus 2 minus 1. But this one 1, 2, 3. 3 minus 1 is 2. So this is not balanced now. This is not balanced. Okay. After adding 27. So let's first add 27. So imbalance is 30. Okay. Insert 27. I will run it step by step. Right. 27 is added. Now that part is done. Now it will check the imbalance. No issue. Balance factor is minus 1. No issue. Balance factor is minus 1. Now it will check the root. Yes, balance factor is 2. So that means there's a imbalance there. Right, imbalance there. Now you can clearly see that it is left-right scenario. The imbalance is here. The imbalance is due to this node. Okay. So you have to look at the reason for imbalance is this node, not this one. So if this is the reason for imbalance, it's a left. But the imbalance is here. And the reason for imbalance is this one. So therefore, it is left-right scenario. Left-right scenario, you have to do 2 rotations. That is first make it left. So that means you take 25 up, 22 will go down, and with 25, 27 will come. So then it will be a left. Then you have to do a right rotation to make it balance. Okay, let's see whether we can see the first rotation. After first rotation, 25 will go there, 22 will go down, 27 will come with 25. Okay. That is the first rotation to make it a left issue. Okay. Right. So 25 goes up, 22 went down. Okay. And 27 came up. Still, this is not balanced. Now the first rotation is done. First rotation is done. Now it is a left scenario. Left scenario. Still the imbalance is here. It's a left scenario. Now left scenario can be fixed using right rotation. But right rotation now you have to do it here, not here, because otherwise it will again imbalance. Okay. So now you have to do the rotation here. So 25 will come here. 30 will go down, but remember when 30 goes down, this 27 has to be taken care of by 30. So this 25's right child will become 30's left child. And of course, these guys will come up. Look at it, okay? So you need a lot of concentration to understand this. So 25 will go up, 30 will go down, but 27 will be now left child of the 30. Okay? Right, you can see 27 become the left child of 30. Now the rotation happens. 25 goes up, and others also came out. 30 went down. Right, done. Now it is right. Now it will check the balance factor. It is 0. Right, done. Okay, done. So that is how you make it balance again. Okay, so you have to do this with the tool and check whether your logic is correct. Your logic is correct. Okay, so then of course after some time you will find that you are comfortable with that. Okay, so let's do just one more. Say I want to add something like 29. right? 29. So 29 will be added here, and then let's see whether the balance factor is violated. So 29 will be added here. Right now, it will check for the violations from that point onwards, upwards. So this one's balance factor is 0. This one's balance factor is -1. Fine. This one balance factor will be +1 because 2 minus 1 is +1, which is also fine. Right? And this one's balance factor will be 2 minus 3, which is -1. That is also fine. So therefore, no need of rotations. This will be -1. Right? So therefore, it is balanced. No need to do rotations. Okay. So likewise, you have to keep doing this. Okay, keep doing this. Okay. And if there's an imbalance, you have to do the rotation to the correct point. Sometimes your first rotation is here, second rotation is here. Okay. So you need a lot of concentration and so on. Okay. So in some years, they have asked you to write down each and every step. Right. For example, which is sort of a need a lot of time also. Second papers. You can see. So you have to explain each and every step after rotation, single rotation, what happens, after the second rotation, what happens, and this is your final results and so on. Okay. Likewise, you have to explain it. Okay, you have to explain it. So this is removal. We discussed how to remove things. Right. So this you can do these questions now. Okay. So there can be a situation where this is not AVL tree, this is the removal, but you have to explain. You found the in-order successor or the in-order predecessor. Now we are replacing with that. So you have to use your communication skills also to explain it. And this is creating AVL tree. Okay, creating AVL tree. So first they have asked what are the possible scenarios: left scenario, right scenario, left. Now you can see left. So left, right, sometimes they call it left dog leg, right? Left dog leg. This is right dog leg or right left scenario, okay? Or crook scenario. So then they have asked you to keep building the AVL tree. So now you can do these kind of questions, okay? Right. So I hope you get it. Any questions? Any questions? So of course the questions will be there when you start doing these things, right? With the help of the tool. Right? Sometimes what you think is not your tool is doing. So remember, tool is correct, then you are wrong. So then you have to identify what's wrong with my thinking. Okay. Right. Right. Now we move on to our final subtopic. That is, okay. So before moving to binary heap, I want to do some more things. Now remember, we discussed about the breadth first traversing and depth first traversing last time. Right. So the depth first traversing can be either pre-order traversing, post-order traversing, or in-order traversing. Okay. So when it comes to the depth first traversing, we implemented the in-order, post-order, and pre-order using recursion. But there's another approach which you must know, and of course they have asked that in the exam also. That is, when you do let's first look at the breadth first traversing, because we didn't do the breadth first traversing. Then we'll come back to the depth first again. Right. So the in-order traversing, post-order traversing, And pre-order traversing are 3 different variations of depth first traversing, because we try to go into the depth, right? Quickly we try to go into the depth. But there's another traversing technique called breadth first traversing, or another word is level loader traversing, which is super easy to understand because we just stay in the next level, we visit all the nodes in next level, and then we visit all the nodes in next level, and then we visit the nodes in next level, and so on. So we visit this one, 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 and so on. If you do like that, we call it level loader or breadth first. So we don't go into the depth, rather we stay in the breadth, or we go level by level, but again, usually we go from left to right in the same level. You visit this and this, okay, and then this. Right. So now let's see how to do the breadth first traversing or the level loader traversing. So the easiest way is you can use, so this is how you traverse this, this, okay. Right. So for example, if you want to do a breadth first traversing for this data, the output is you have to, they ask you that kind of questions as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is the result of breadth first traversing or level load traversing. Now, how do you implement this? How do you implement this? So there's a very easy approach. Of course, you can use a recursion also, right? Recursion. You have to implement both these by yourself. I don't do the implementation, but I will explain how to do it, because you have the queue. You have the queue implementation. You have to use the queue implementation code. For the other one, you have to use the stack implementation code. Those code you are having now. You can copy that your queue class and the stack class, and then implement these, because you need the queue instance and stack instance. Queue instance for the breadth first traversing, stack instance for your depth first traversing. Okay, right. So this is how you do it. I will explain the logic only. In the exams, usually you don't have to write the code. You have to explain the logic. Okay, it's all about communication, right? Remember, programming language. So basically, can you communicate your solution first to a human, then to the computer? Okay, so to a human, pretty much you write the algorithm at high level. To the computer, you implement it using the language of your choice, Java or Python or whatever. Right, so this is how you do using a queue. That is how to do the breadth first or the level loader traversing. You start with the root and you print it. Okay. So then you take that to a queue. You know, queue data structure, first in, first out data structure. Whenever you visit a node, you put it into the queue. So therefore now your queue has root and you have visited and you have printed that value. Okay. So that is your first step. Okay. Visit the node, which usually just means printing out the value. Then add the node's left child to the queue, add the node's right child to the queue also. Now you have to add your left child and right child to the queue. That is, in this case, D and K. Right? So now D and K is there. Right? D and K is there. Okay, D and K is there. So what is the next step? Once we do these 3 things, we can remove the node from our queue because we don't need anymore. Now we have to take one from the queue. Always what you take is the first in. So now you have already added D and F because it's a binary search tree. So you have a maximum 2. Now you have to take one from the queue. That will be the first one inserted. That will be the F. Now you have taken F out. Right? Taken F out. Earlier F, D and K was there. Now F is not there. Now your queue has only D and K. D is in the front, K is behind. Okay. So now you have to do this again and again. Now again you visit D now. When you visit D, you have to add its two children to the queue. So therefore E and B will be there, then E will be there because you have visit D. Then again you take 1, which will be K, right? And you print that, already you have print that. Then you have to add its two children, G and L, G and L to the queue, right? So now you have taken a K. Now you have to take B out and you have to add A and C to the queue. But now you have taken B out. And likewise, you keep doing this until your queue is empty. When your queue is empty, you have visited all the nodes in level order or breadth first manner. So you must be able to implement this and see whether the output is F, D, K. First of course, we have to create your binary tree because that we have already implemented. Insert method. Of course, you can use numbers. So the final results must be in this case F, D, K, B, E, G, L, A, C, H, J. Okay. So super important that you implement this, right? It's not rocket science. If you are already familiar with these queues and those things, because you have the implementation code, you can reuse it. That is what software developers do. Software developers don't implement everything. They reuse. They just concentrate on solving your current problem. Right? You don't want to solve go to the atomic level and solve this, right? Transistor level and solve problems. No, right? If there's someone who has solved this problem, again, of course, in that case, what we do is in this kind of a situation, we will just search for the breadth-first search code and reuse it. But don't do that because you are learning things. Okay, you are learning things, but you can reuse the code I will be sharing to you, including the search and everything. And you have the queue implementation. For the next one, you need the stack implementation. Reuse those code and implement the breadth first or the level order traversing by yourself. Right? So it's a very good exercise because we want to build your character. We want to build your confidence so that you go to interviews, go anywhere in the world and live. Right? Of course, plenty of software developers, right? More than 90% of the software developers in Sri Lanka, after sometimes they live in some other country because they don't fear, because they know they how to do things. Right. So that is how the breadth-first traversing is implemented using a queue data structure. Right. Breadth-first traversing implemented using queue data structure. Right. So the next, I will explain how to implement a depth-first traversing using stack data structure. Right. Stack data structure. Right. So we will do the pre-order traversing using stack. Right. Pre-order traversing, sorry, this is pre-order traversing using queue actually. Post-order traversing you can do using queue, sorry, stack. Okay, so this is using, sorry, this is wrong, right? The typing mistake, it must be not using queue, pre-order traversing using stack. Okay, right. So this is how you do it. So first you want to traverse to the root. Always we start with root. Right. So then you go to its left child and you put it there. Right. Remember, pre-order traversing is current, left, right. So current, left, then current, sorry, current, then left, right is not there. Then you come to the right and say current and so on, right? So every time you visit, you put it into the stack. Right? Every time you visit, you put it into the stack. And when you run out of options, you pop it. You pop it. So therefore, again, you will keep popping up to this point, and then you will go to 5, then 6, then you pop it, then 7, and so on. So you keep going like that and come back, and then go like that and come back. When you go like this tree, again, you will come back and visit this tree, and so on. So you keep pushing things and popping things, right? So when you have nothing to do, you have to pop it and see whether you can go in that path, right? So I just explain it at high level only. So again, see whether you can understand it. So how do you understand it is, take your stack code, right? Now this time you can't use recursion. You have to use only the stack data structure and implement the depth first traversing. Okay, so ultimately what you get is the same output you must get 1, 2, 3, 4, 5, 6, 7. That is pre-order traversing, right? So pre-order traversing you can implement either using recursion or you can using a stack. Then breadth first traversing or the level order traversing you can implement using queue, right? So pre-order traversing you must implement using stack. Breadth first traversing you must be able to implement using queue. So take it as an exercise, because you have the queue implementation and stack implementation, you must be able to do it. Okay, so if you manage to implement it, you can post it to the WhatsApp group or to me with your test code as well, right? With test code and all other code, put it into a zip file and post it, so that if someone is struggling to implement it, so that guy can get the help. But don't look at others' code. Look at others' code as your last solution, right? Your last solution. So you must be a fighter, right? Right. You must be a fighter, because if you become a software developer, you can't නේද අඬාගෙන ගෙදර ඉන්න බෑනේ 12ට විතර මට බෑ මේ වැඩේ කරන්න කියලා නේද එහෙම software developers නැහැ නේද එහෙම අයත් ඉන්නවා හරි ඒ කියන්නේ එහෙම අය සාමාන්‍යයෙන් field එකට එන්න හම්බ වෙන්නේ නැහැ interview දාලා ගන්නවා එහෙම බෑ ඉතින් you must be a fighter. Of course you can get help from others, but you can't get help forever, because they also have their task to do, right? So therefore, of course, after sometimes you have to help others, because there can be some junior developers who are looking for help from you guys then, because you become more matured, serious, seasoned problem solvers after sometimes. Okay, so likewise, after sometimes you must be comfortable. For example, if I'm supposed to implement this, I can implement this, right? I can implement, I have no issue with this. Maybe it will take a little bit of time to understand or comprehend the solution. Maybe the first implementation may have a bug, right? Maybe I can fix it after testing. So likewise, so then at the end, I can go home without any stress, right? Right. So just implement that pre-order traversing using a stack, breadth first traversing or level order traversing using a queue. Okay, just keep it as exercise. Right. So now let's look at few more usages of binary search trees. Of course, binary search trees main usage is what? You can keep it in a search tree and do the searching fast. Right. You keep when you insert data, you just insert into a binary search tree, so that when someone is looking for something, you can search it fast. Right. Log to n times you find it. Log to n time. Remember, log to n is later we will learn about the linear search. Linear search, it's on compared to on linear search. If you keep the data in a binary tree, it is log to n. So on is something like this. Log to n is something like this. When you have millions of data, this is much better performance than linear search. Linear search means you keep it in array or something, you keep searching. In the worst case, if you have million data, in the millionth iteration, you find the data. But when you have millions data in binary search tree, it is not million, it is say you have 1024 data. In linear search, the worst case, you found it in the 1024th iteration in your loop. But if you put it into a binary search tree, you have 1024 data in level 10 levels, because log 2024 is 10. So your binary search tree will have only 10 levels and you have 1024 data. So the worst case is your data is in the leaf, still in 10 steps, because we just go left, right, left, right, left, right. So the worst case, in 10 steps, you find it. So finding something in 10 steps is faster than finding something in 1024 steps. So that is why we say log to n algorithm is better than n algorithm, or log to n algorithm is better than ON algorithm. ON algorithm is linear search. If you keep it in a binary search tree, it's a log to n algorithm. The search is a log to n algorithm. And there's another advantage when you keep it in a binary search tree. If someone asks you to print it in, give it in the sorted order, you just do an in-order traversing, right? And when you do the in-order traversing, you are giving the result is sort. That means it's already sorted. The data is already sorted. So two advantages: data is already sorted because when you run the in-order traversing, you get the sorted order. And search is super fast. Not, I can't say super fast, but compared to the linear search, it's super fast because here iteration is 1024 times. Here you have only 10 iterations. Your loop will execute only 10 times, and either you find it or you can say no, it's not there. Okay. But only thing is you need more memory because if you keep it in an array or something, you need just 1024, say 1024 data, you need 1024 memory location. But here, every node is keeping track of its left child and right child. So therefore, every solution has pros and cons. So if you keep it in a binary search tree, you need more memory. But insert, search, sort is fast. Okay, fast. Right. So that is obviously the main usage of binary search tree. Keep your data in a binary search tree so that you can, in no time, you can give it in the sorted order, and also you can do the search very fast. Now let's look at some more usages. Okay, some more usages. Right, another usage is, remember we discussed about keeping our expressions, infix notation, prefix notation, postfix notation. Right? Infix notation, prefix notation, and postfix notation. Or we want to convert an infix expression to a maybe postfix expression or a prefix expression. So how can we do that? So there's a way to do that using binary search tree. Okay, using binary search tree. Right, how to do that? Now let's say this is my expression, put it into a binary search tree. Okay, say this is my expression, A into B plus C. So how do you put it? A into B plus C. Now I want to get the, say, postfix expression. How do you get the postfix expression? You know how to get it. A, you need two operands before the operator. So I'm waiting for the next operand, but I can't evaluate it until I do this. So therefore it will be B, C plus. Now I have the second operand, the first operand. Now I can do the multiplication. That, of course, as a human, intelligent, smart human, we can do it once we understand the logic. Right? But how do you explain it to someone? Right? Say, when the infix notation expression is given, you want to write a program that converts your infix expression to a postfixed expression. Now, how do you write the logic? How do you write the logic? Okay, because now you have to write the logic. So, binary search tree can help. Or binary tree, not binary search tree, binary tree can be used to convert infix expression to a postfix expression. So what is your task is, you insert your operands and operators, both operands and operators, to a binary search tree from left to right, A into B plus C. Now, if you want to get the postfixed expression, you do a post order traversing. post order traversing. What is post order traversing? Left, right, current. Right, left, right, current. Post means that, right? Go to the down, then come back. In order is left, current, right. Pre-order means current, left, right. So post-order means left, right, current. Right, left, right, current. So let's do a, now this is, we just added as it is the infixed expression. Now if you do a post-order traversing, you will get the post-fixed notation. Okay, let's do the post-order traversing. Left, right, current. When you say current only, you print, remember? Right, so you start with the root, left, then left, right, current. Okay, now you came left, you have to go right, again left, left, right, current. You came left, right, current. Now you have come left and right, current. Now for this guy, you have come left and right, current. Remember post order, and you can see that that is a postfix expression. That is a postfix expression. So when you insert your data into a binary tree and do a post order traversing, effectively you have converted your infixed expression to a postfix expression. So that is another use of binary tree. It's not a binary search tree, it's a binary tree. Okay, so let's do one more exercise for that. Let's say I have this A plus B, sorry, A into B plus C plus, or let's say minus D. Okay. So let's put it into a binary tree. So this is a little bit tricky. Okay, so this is A into B plus. Okay, so let's say this one, because this is plus and minus has the same level of thing. Okay, so therefore let's make it something a little bit more interesting. A into B plus C A into B plus C. That means you have to do the multiplication after this. Okay, multiplication after this. Then let's say again add D. Okay, again add D. Right. So now how do you write it? In the infix notation. Let's put it in the infix notation first. Then we'll see whether post order traversing results in the postfix notation. Okay. So you need A into this is B and C plus B plus D into A. And then you need D here. D here. But then you need add plus. Okay. So A into B plus C plus D. Right. A into B plus C, that plus D, because that is the result. Okay. So this is, you put it into you put your expression into a binary tree. It's not a binary search tree, it's a binary tree. Now, if you want the postfix notation, what you have to do? You have to do a post order traversing, right? So let's first do the post order traversing, and okay, let's first write the post order postfix expression. Then we'll do a post order traversing and see whether we get the same, right? So this is how you do it. A, B, and C you have to add. Then those two we can multiply. Then you need D and add. Okay, so that is my postfix notation expression using as a human, using my IQ. Now let's do the post order traversing and see whether we get the same. Right? Left, right, current. Post order, right? Left, right, current. Left, right, current. Then I came left, right, left, left, right, current. Right. So then I came left, right, current. Now I have done the left, right, current. Now I have done the left, right, current. Now I have done the left, I have done the right, left, right, current. Now I have done the left, right, it's current. And you can see I got the answer. Right. So I got I got it from as a human, my understanding about the post-fixed rotation, and then I just insert this into the binary tree and let computer do the post-order traversing, and I got it. Okay. So therefore, if you put it into your infix expression into a binary tree, and then do the post-order traversing, what you get is post-fix expression. Okay, so that is another way of converting infix expression into a postfix expression. Because remember, in computer, we always use postfix expressions, and then using a stack, we can implement this. That part we have done. How to evaluate a expression using stack, we have done in stack topic. So therefore, now you can see a lot of things are getting interconnected, right? And using different data structures in a smart manner, we can solve different problems. Of course, we will not be able to solve all the problems in the world, but every problem, right, we may be able to connect into different data structures and solve it. Now, when we do the graph data structure, you will find it even more interesting, because most of the problems in the world are actually graphs. If you take something like your Facebook, it's an interconnection of friends. Right? Interconnection of friends. It's not a binary search, it's a graph. If you take Google map, all your traveling is done using a graph. So they will find what is the minimum path, which is the fastest path. So those things we'll be doing when we are doing the graph. Okay, graph is even more challenging, and it's most interesting and more useful than tree. Of course, tree has some usages. The graph has even more practical usages, and how to optimize those things is another interesting area. Okay. Right. So those are some usages of tree data structure, or the binary search tree data structure. Right. So we have already discussed the balanced binary trees, or the AVL tree. Right. So now we are done with binary tree or binary search tree. Our next topic is binary heap. Binary heap is again a special kind of a binary tree. Now, remember, we first discussed tree. Then we look at a special case of tree called binary tree. Then we look at binary search tree. Search tree. It's sorted from left to right. Now we look at a special kind of a binary tree called binary heap. Here it is binary search tree or binary sort trees sorted from left to right. Binary heap is sorted from top to bottom. Okay, so that is what binary heap. And also we learned a special kind of binary search tree called balanced binary search tree under that AVL tree. So you can see balanced binary search tree is a special case of binary search tree. Binary search tree is a special case of binary tree. Binary tree is a special case of tree. And now we look at a special case of binary tree called binary heap, which is sorted from top to bottom. Here it is sorted from left to right, binary search tree. Okay. And so we'll take a break. After the break, we'll look at binary heap because it's very easy. Okay. Right. So now it's 10:25. We'll be starting at 10:40. And it will be binary heap. So then the tree. Right. So now we'll move on to the binary heap. So as I told you, binary heap is again a binary tree, but it is sorted top to bottom. Okay, ascending or descending, that is up to us. Okay, but when you make a binary heap, there are some more prerequisite we have to follow to make your binary heap efficient. Okay, Right. So what are those additional constraints we have to preserve when we are creating a binary heap? So the number one is the shape property. That means your binary tree must be a complete tree. We discussed the complete tree previously, right? Earlier, the complete tree and full tree. So binary heap must be a complete binary tree. Complete binary tree means it has to fill from left to right. It fill this one and go to the next level, and again next level also it has to fill from left to right. So that is called shape property. Okay. And of course, the heap property is straightforward because that is why we call it binary heap. It must be sorted from top to bottom. So that means if it is maximum in the root, then your child must have a lesser value than your parent. That has to happen for each and every node. Your children must be lesser than your value. It has to happen for each and every node. So that is called heap property. And again, if the maximum is in the root, we call it a max heap. If the minimum is in the root, we call it min heap. So min heap is sorted from top to bottom, minimum to max. But max heap, the maximum is in the top. Okay. Right. So you have to make sure that your heap property is preserved, shape property is preserved when you insert. Right. Right. So how do you insert to a heap? Okay. How do you insert to a heap or binary heap? So it's a 3-step process. So these are the 3 steps. Always your new node must be added to the last level, preserving the shape property. Right? Preserving the shape property. So then you have to compare your new node with your parent and preserve the heap property. First, you preserve the shape property. Then you have to preserve the heap property. That means if your newly added element, if it say it's a max heap, if the newly added element is bigger than your parent, there must be a swap because you want to take it up. Okay. Then you have to compare it with its parent and so on until the heap property is not violated. Okay. So if there's a violation, you have to do the swap, again check, again do a swap, again check. So when there's no need for swap, you can change, you can stop. Okay. Right. So I know that still it is not very clear. So the best way is let's do it as practical exercise. Okay. So again, I will be using this particular tool. I will again go back to the original page. That is /en. Okay. So then there's something called binary heap. Okay, binary heap. We'll get into the binary heap. Okay, binary heap. Right. So let's create a small binary heap first. Okay, let's create one by one. Okay, so let's create empty one. Let's say we have only 50 here. Just one node. And that will be your root node. Okay. Right. So now let's say we want to insert 80. So remember, you have to preserve the shape property. So therefore, 80 will be added as the left child of, because you have to go from left to right, as the left child of root. Then it has to check the heap property or the sorting order. Okay. So it is added as left child, then check the heap property. This is a max heap. So therefore, 80 is bigger than 50. Therefore, it did a swap. Right? You can easily understand this, right? Right. So now let's add another one. Say I want to insert, say 30. Now it's a binary heap, so therefore it has to preserve the shape property. So therefore it will be added like this. Okay. So then it has to check the heap property. Obviously 30 is smaller than 80, therefore no need of a swap. And therefore that will be the end of that. Okay, right. So let's do the animation and see. 30 is added. There's no need for swapping. Now remember, this is not a binary search tree. So therefore, don't think that you have to go left, you have to go left. That is binary search. This is a binary heap. You always initially you add your node preserving the shape property. You fill from left to right, right? Don't think that you want to go to the correct position. That is binary search tree. This is a binary heap. Right. Now let's say I want to insert say 70. So now this level is filled. So therefore now I have to again go to the left side because I have to preserve the shape property. Then I have to preserve the heap property. So now I have to compare with its parent. Yes, your parent is smaller, therefore you need a swap. So 50 comes here, 70 goes there. Then you have to again compare it with your parent. No need because 80 is bigger than 70. So therefore that's it. Okay, that's it. Super simple. Okay, so this is super simple concept. So let's insert 70. Go. First shape property is preserved. Now heap property is preserved. Done. Right, done. Okay, now let's say I want to insert, say 85 or let's say 75. So 75 will be added here, preserving the shape property. And 75 is bigger than 70. Therefore, there will be a swap. 7 will come down, 75 will go up. Okay. So now swap. Okay, that's it. Now let's insert another one. Say I want to insert, let's assume I want to insert 100. First, it has to preserve. I'll just stop it. Sorry. I want to insert 100. So 100 will be inserted as the left child of 30 to preserve the shape property. Okay. Go. Okay, so 3 digits is not allowed here. So therefore, let's call it 90 because this doesn't allow 3 digits. And go. Right. So now you can see 90 is here, preserving the shape property. Now it has to preserve the heap property. 30 is 90 is bigger than 30. So therefore, it has to do a swap. Okay, it has to do a swap. Let me do the swap first. Right, I'm going step by step now. Right, now it has to compare 90 with 80. Obviously, 90 is bigger. Therefore, again, you have to do a swap. Right, now we are done. Right, always the biggest value will be in the root, and next level you have smaller guys. Next level you have smaller guys. For example, these two must be smaller than this. And these must be smaller than this. And there's no need, for example, there can be 70 here, 50 here. That is perfectly okay. So there can be 70 here, 50 here, because you don't need left to right sorting. Okay. Only thing is you need top to bottom sorting. That's it. Okay. So therefore, that is fine. Right. So now let's see, I want to insert, say, 20. Right, 20. Now, to preserve the shape property, it has to come here. Then it has to preserve the heap property. But it is also okay because 80 is bigger than 20. So therefore 20 will stay there. So there's no need to 20 to go here because this is not a binary search tree. This is a binary heap. Okay. So let's insert 20. 20 is added there. And nothing to do, right? Nothing else to do because it's perfect. Okay, right. Now I hope you got it. Now let's add only maybe just one. Say I want to insert 35. Of course, now 35 has to come to the left side of this, and that's it because the shape heap property is preserved. And that's it. Right. So let's add one more. I want to add 85. Right. 85 will be initially added as a right child of this. Right. Right child of this. Now it has to preserve the heap property. 85 is bigger than 50. There will be first swap. Right. First swap. Now it will compare with 75. 85 is bigger than 75. It has to do another swap. Okay. 85 is not bigger than 90. Therefore, that's the end of the story. Right. You stop it. I hope you got it. So that is how you keep inserting. Right. You keep inserting. So you can take a piece of paper, insert some data to the max heap in your piece of paper. Then you use this tool and keep inserting and see whether your max heap is as what you draw as the max heap and what you get from this tool is the same. You must get identical thing. Your solution and the solution generated by this tool or any other max heap tool must be identical. Okay, identical as long as you insert in the same order. Okay, right. So that is how you insert. Okay, so we don't have a lot of operations. So again, we don't do the implementation. Of course, if you want, you can do the implementation. It's a good exercise for you guys because that implementation is very easy. I can't say very easy, but it's doable. Okay, but it's challenging because the second part is easy. That is preserving the shape property is easy. But again, you have to go backward. Unfortunately, we have references to the downwards, right? Therefore, it is not actually, that is not that easy. Yeah, I would say it is not that easy anyway. But implementation is possible. So that is why this tool has been developed. But again, yes, I agree that it is not that easy. You need a little bit more thinking, and there are multiple ways of implementation as well. Because first of all, you have to identify where to add the element. So that means you have to find the last level, the correct place to add this. So that is the difficulty. Right? That is the difficulty. So then, of course, you have to do the swapping. So in order to do swapping, usually this guy has access to this guy, but not this guy has access to this one. So therefore, again, it is challenging task to find your parent because parent has access to children, but child has no access to parent. So therefore, you need to come up with some tactics to counter this. Okay, but it's doable, but it's not as simple as that. Okay, because you have to do the swapping there. Okay, right. So see whether there are some possible implementation if you are really interested, but it will be a little bit more complicated than what you think. Right. So that is how you insert. So the next task is delete. Delete. We have only two tasks: insert, delete. Right. So delete is always, you don't delete randomly usually, but of course you can delete any element as well. But what we want to implement first is delete the root. So that is what we do. We always delete the root. Okay. So I will tell you why later. Okay. I will tell you why we delete the root. Now this is how you delete the root. So delete the root means in this case we have to delete 90. So this is how you do it. You take the last level rightmost element and replace that with, because anyway we are going to take this out, 90 is out, but now you can't just make it a whole. Okay, so you have to fill with some value. What we do is you go to the last level and the rightmost element and replace that with that. So that means 50 will come here. Anyway, 90 is now out because we take it, remove it. Now 50 is no longer there. We have to replace it here. But after doing that, now you may have violated the heap property. So now you have to fix it. You compare it with your child, right? And if your child is bigger than you, now you have to do a swap. Okay, right. So let's use the animation to explain it. Now I want to delete the first element or the root element. Okay, we delete the root element. Okay, I delete. So I'll say I value is the first element. First element is a root element. Again, I will do step by step. Right. So I want to delete this. Okay. Now I took this one and going to replace this because that is the last level rightmost element. Okay. Replace. Okay. So now this element is removed, replaced by that element. Now you have to do the check the shape property. So 50 will be compared with 85, and of course 50 is smaller, so therefore you have to do a swap. Okay, right? So you have to do a swap. Now again you have to check it with 75. Of course 75 is bigger, so therefore you have to do another swap. Okay, another swap. Of course 70 is also bigger, but you check it from left side. Okay, now you have to compare it with 35. Of course, 35 is smaller than 50. So therefore, you don't have to do anything. Now you are done. Now remember this earlier, the root is now no longer there. We took it. And now we are done. Nothing else to do. Okay. Right. So now we always remove the root. Now we want to remove 85. That means again, the first element. Right. First element. Right. So now it is replaced by 35. Right, 35. Okay, let me backward and explain it again. Right. So I want to remove this one. It is replaced by 35. Okay. Now it is replaced by 35. Now it has to compare this with this. Of course, 75 is bigger than 35, but 80 is also bigger 35. Therefore, now you have to, if both are bigger, you have to swap it with the bigger guy. Why? Why? Because if you swap with 75, then 75 when 75 comes here, then 80 is bigger than 75. Right? So if you do this swap, because 75 is bigger than 35, then what will happen is 75 will come here. Right? 75 will come here and 35 will go down. But now again, against heap property is violated because 80 is bigger than 75. Then again you have to do a swap. So therefore, rather than doing a two swap, what you have to do is when you compare with both left and right elements. You compare with both left and right element and swap with the bigger guy, because then it is just one swap you have to do. So therefore, the bigger guy is not 75, 80. So therefore, you do the swap here. Okay. So therefore, the next step is swapping 35 with 80. Right. And then you have to compare 35 with 30. Yes, 35 is bigger. 35 is bigger. So therefore, that's the end of the story. Nothing else. Okay. Right. Now let's remove 80. 80 means the first value. Go. Right. So we have to replace it with now 20. Okay. 20. Because that is the last level rightmost element. Right. You replace. Now you have to compare. 75 is bigger, 35 is bigger, but 75 is the larger one. So therefore we swap it 75. Okay, 75. Right. Now you have to compare with the other two. 50 is bigger than 20, 70 is bigger than 20, but 70 is the bigger guy. So therefore we swap it 70. Right. We swap it 70. And now again you have to compare with, now we are done actually, right? Now we are done. Now it is again our max heap is preserved. Right. right? So I hope you got it, right? You got it, right? So then someone will ask, what is the use of this? So the use of this is, when you create your max heap or min heap, whatever, when you keep taking from the root, what you get is the sorted data. Because next time you will take 75, then again the biggest guy will come here, then you take that. So when you keep taking this until your heap is empty, basically you have got the data in the sorted order, right? You get the data in the sorted order. Actually, we are not keeping the data in the sorted order, because this is 70, this is 35. You can see this is 35, this is 50. Right? So 75 is the biggest, that is okay. Always the root has the biggest. But you can see that here you have 35, here you have 50. So therefore, when we say it's sorted this way, it's relatively. Okay. Only thing is, these two are smaller than this. But it doesn't mean that you don't have smaller guys in the previous level. You can see. So therefore, when you take these items, we always preserve the heap property, so that ultimately you have got the data in a sorted manner. So that is why I told you that usually what we do is what? We always take from the root, because that is how you keep getting the sorted data. But theoretically, if you want, you can remove any node. That also you must know. Okay, so next one, what we want to remove? 75. Next time, what we want to remove? 70, because basically what we want to remove is the root until your heap is empty. So that means you have got the data in the sorted node. But you must know how to remove any node as well, but that is not part of the heap sort. Okay, so therefore now, since we have deleted a lot of things, let's create a new heap. Say we have this particular heap with some more data. Let's say 29 and 50. And so let's create it. Right, so this is the heap. Let's do a little bit of arrangement again. So that means it has already added the data, and now it is fixing the issue. Okay, so that is why it is taking time. It is not fixing each and every step. Okay, now it's a heap. Right, now it's a heap. Now let's say I want, of course, you know how to delete from the root, right? So you know how to delete from the root. 90 will be replaced by 17. Then it will preserve the heap property. Okay. Okay, let's do just one for that. So I want to delete the root, which is I equal 1. Okay. So I will do it step by step so that you can see. So this will be replaced by 17, because that is the next right element. Okay. So 17 will be used for the replacement. Okay. Then 50 will be used because 50 is bigger than 36. There will be swap between 50 and 17. Right. So then 26 is bigger than 17. So therefore, there's another swap. And that's the end of the story. And we have now a new binary heap. But that is removing the root. That you must know now. Right. You must understand how to do that. But now let's assume. So that is what we do in heap sort algorithm. So in sorting algorithm, you have a sorting algorithm called heap. Actually, now we have already done that. Right. Sweep sorting algorithm. So actually, now we have done 2 sorting algorithms. Sort using binary search tree, that is doing the in-order traversing. Sort using binary heap, that is insert the data and you keep taking from the root. So therefore, you have already learned 2 sorting algorithms. Right. So when we implement the sorting algorithm, we always take the root. But for some reason, let's say we want to remove some other node. Maybe we have added by mistake and now you want to remove it. That can be the case, right? So while your data is in the heap, you want to delete it. Delete the element, but not your sorting. Say I want to remove 36. Okay. So now what we have to do is, first you replace, this is not part of the sorting. Now you again have to replace, remember the last level rightmost element is this one. You have to first replace this with this. Okay, that is your first step, because ultimately you want to delete this. Okay, so that means you would basically delete it, but then again you have to preserve the heap property. Look at it. Okay, so this time I'm not taking from the root because I'm not in the part of, I'm just deleting odd data, not doing the sorting. Okay, so I want to delete. Here we have the I value 2. I am not giving the number, that second element, index 2 element. Okay, so therefore I want to delete 36. That is second element. Again, I will do it step by step. Okay, so that is why I want to delete 51. So it will be replaced with 2. Look at it. Okay. Sorry. First, sorry, I made a small mistake. So this is the one I want to delete. First, we take it to the root by swapping. Okay, because now 51 is in the root. Now only we do the swapping. Right? Now only we do the swapping. But swapping is always done with this. Okay, so I made a small mistake there. Now you have to preserve the heap property. It will be compared with 50 because 50 is bigger than 26. There will be a one swap here. There will be one swap. Then again, 2 will be swapped with 29 because 29 is bigger than 25. Okay. Then there's another swap between 90 and 2. Okay. Right. So that is how you delete it. Okay. So that is deleting a middle term, right? Middle term, not deleting the root. Okay. Now let's do another one because last one I made a small mistake. Right. So let's say I want to delete, say 25. 25 means fourth element. Okay. Fourth element. Look at it. Okay. Stop it. Now this is the one I want to delete. Okay. This is the one I want to delete. This is the one I want to delete, the fourth element. Okay. Why does it make it to a 51? That is my confusing because it's 25. Why it is making it to something else? Is it a bug? You can see it's now 51, right? Why? That is a strange thing. Right. So that step we can understand. So my question is why. So that part I can understand, we can explain. So let's do another one. Say I want to delete, say 17. 17 index, sorry, not 17, 6th index. 6th index. Go. Right. So why is it all of a sudden become 51? That is my question. I think it's bigger than this one, right? So that it can go there. I think that is what it does. Okay, we can double check in the next step. Right. So now it goes there because it want to make it the root. Okay. Now it comes to the root, and now root is replaced with this one because that is the last level rightmost one. Right, you can see. Right, so now it has to do the swapping. It will swap with 50, and then it will be swapped with 26. Okay, and that's it. All right, I think it make it one bigger than this one when it want to delete something. Okay, let's say I want to delete 7. Okay, I want to delete 7. Right, 7 in the sense the fourth index. Okay, fourth index. Now the current fourth index has 7. Right, now you can see it make it as 51 because just it want to make take it to the, of course, that is the one we want to delete it, but we just think that it is now, it must be the root, new root. Obviously, we are not deleting 51, we are deleting that value, but just we temporarily thought that it is bigger than 50, so that it ended up as the root, okay, new root. And it has to do the swapping now, right? Now, we think that, of course, this is not 51, the original value is the one that delete, but now we have to replace it with 2 and do the normal deletion, okay? Normal deletion. So that is what we do. Okay. So that just take it as something bigger than the root value so that it can end up as a root, and then you do the normal deletion of the root. That is the strategy. Okay. Right. So we'll do one last deletion. Say I want to delete, say 3. 3 means index 6. Index 6. So it will mark it as 51 now. Okay. Temporarily. Right, 51, so that it actually now that data is deleted, okay, because after ultimately 51 will be deleted, but 51 means the original value, okay. So now it has to swapping and it will end up as the root. Now it will be replaced by this one, because that is the last one in the last row, right? You can see now it has to rearrange the sorting order. 50 is bigger, therefore there will be one swap here. Then 26 is bigger, there will be another swap. So that is how you delete a middle element. Middle element. Okay, but in sorting, what we always delete the one by one, the current root, current root, current root, current root. At the end, your data is sorted. Right. Right. So I hope you got it. Okay. So again, the implementation is not needed, but you must be able to explain how it is done. Okay. Right. So that's it about the heap. Okay. So delete the last, the delete in the root or deleting a middle element. Okay. Deleting a middle element. Right. So that's it about trees. We discuss the binary search tree, binary heap tree, binary search tree and binary heap tree. So then you have general trees. Right? General trees. So general trees are having a node having more than one children. So far, we have restricted it to maximum two children. But if you want, you can have something like this. So then we call them the general trees. Again, you have two type of general, you can't say binary then, general trees, that is B minus tree and B plus tree. Okay. Right. So we'll look at the B minus tree and B plus tree next time, and then we'll move on to the graph, and then data structures are over. Then we have the searching and sorting algorithms. Out of those two sorting algorithms, we have already done, right? And one searching algorithm is also done, binary search. So therefore, we can finish it very quickly. Okay, right. Today we'll not do the object-oriented SAD past paper discussion. So we'll stop at this point. So the next time we can finish the trees. Of course, another 15 minutes. Then we can start the graph. Graph data structure. We don't do the coding much. Okay, actually, we don't do any coding at all. We just look at the algorithms only. So therefore, it will be faster than trees. Okay, right. We stop at this point. Right. Thank you.